Hello. In the previous video, I gave you this example. If I do a food truck, then how can I calculate my potential cost, my cost and my profit? So then the answer is we have to know the cost parameters and we have to estimate them from the realizations. So suppose that this is our data. The unit is just I choose a random unit, and I observe 12 months of the operation of the farm or the factory or the food truck, whatever, and I observe the output in each month and cost in each month. So for example, in January, I produced 2 tons of hot dogs, and it costs $15,000. And in February, I produced 3 tons of hot dogs, and cost also $15,000. So this is from the financial sheet of my farm, but it does not say. Still, I don't know what is the fixed cost and what is the marginal cost. What we want to know is those parameters, marginal cost and fixed cost, and we are going to study how to estimate the cost parameters using this kind of data. Of course, this is an imaginary data, but just assume that let's guess what we do. By the way, it's not easy to understand because, for example, in January and in February I produced 150% of what I produced in January. But the cost was the same, which is a little bit contradicting, obviously contradicting to each other, but it happened. I allow that this may happen because of random error. There may be some random error, so I had a very bad shock. Somehow I wasted too much materials in January, so the cost was greater than I estimated. Or similarly, in May, I produced 6 costs with cost of $20, but in June I produced less but costs more. So these kind of things happen in reality. So we do allow these kind of noises. We assume that they are noises. So let's see. The numbers, there are 12 by 2 numbers. It is not easy to see what's going on in this number table. So we draw the scatter plot. You put output on the x-axis, horizontal axis, and cost on the vertical axis. So when you produce 1 unit, your cost is about like 9. When you produce 2, 15. When you produce 3, also 15. And interestingly, there are 2 observations that produced 4 units, equally 4 units in 2 months, but their cost was different. Similarly, there are 2 months I produced 5 units, but their costs are different. And somehow cost decreases when I produce more than increase in this way. So, by the way, there are only 12 observations, but you see clearly there is some kind of trend, which is pretty clear. Even if I said there are some irregularities, like these 2 points are the same, and there is a decreasing pattern here, and same amount results in different costs. But still, even if there are some noises, but the trend, overall trend, is clear, right? Then what we are going to do here is we are going to set up a model like this. This is called linear regression model. We set up a model that simplifies what we consider, and the linear regression model is usually the left-hand side is denoted as y. This is the variable we are interested in. We would like to predict. In our example, this is the cost, total cost. and beta 0 plus beta 1 times x. So beta 0 is the fixed cost. So regardless of your production amount, you have to pay your cost increases by beta 0. So beta 0 is the fixed cost that you have to pay upfront no matter how much you produce. And beta 1 is the marginal cost. So every unit of X you produce, you have to spend beta $1. That is marginal cost. And X is the quantity, output quantity. Epsilon is the error term or disturbance term, called many different names. It is the noise. This is the noise. So because of this noise, the cost may decrease even if the quantity increases. So many strange things may happen, but we don't know what's going on there, but just we assume that they are errors. Here, and I explained the properties of each variable. So y and x are our observation. So from our data, we have data about output and cost. So we know how much we produced in each month, and we know how much we spent in each month. That's output and cost. And in particular, we are interested in the cost. We are interested in predicting how much it will cost when you produce a certain number of amount. That is our the purpose of doing this. The purpose of using this regression model, predicting the cost given output. But beta 0 and beta 1 are the main parameters of interest. So y and x are observed variables. They are random variables, but beta 0 and beta 1 are constant. They don't change. They are parameters, underlying parameters. They are always the same. So of course we assume that the parameters are the same across 12 months, but they are unknown. So fixed cost and marginal cost do not change across observations, but they are unknown. They are constant but unknown. So they are the parameters of our interest. We are going to estimate beta 0 and beta 1. We will study how to estimate them. Finally, epsilon is the error term. It is unknown. We don't know, so from the data, we don't have the information about error terms, how much error we have. So it's unknown. Also, it is random. The error may be different from one observation to another. So it is that's the typical. That's what an error term implies. So it's easy to understand. So simply speaking, we would like to estimate beta 0 and beta 1 using data on x and y. So this is the simplest possible linear regression model. Later, you may include more variables. You can make it nonlinear, and you can extend it to many different cases. But we are going to study this model for a while. And I'm going to show you a little more examples. Similar examples, by the way, there are a lot of examples you can think of. And I'm just giving you some typical, most fundamental examples in economics. Like first, demand or supply function. Quantity is assumed to be a linear function of price. So when price increases, demand decreases. So then beta 1 would be negative. But if it was a supply function, when P increases, Q must increase in the supply function. So anyhow, have the same structure. We observe the quantity or the price. We observe how much demand if we set price at certain level. And there is an error. And what we are interested in here, we are interested in beta 1. Typically, we are interested in the elasticity of the demand. So the elasticity determines a lot of things, like for example, monopoly price, or how the tax burden is distributed, and yeah, something like that. And like consumer surplus, for example. Okay, this is just an example. And second example, Keynesian consumption function. Consumption C, household consumption C, is a function of household income, right? If you earn more money, earn more income, then you tend to spend more, consume more of that. So in this case, beta zero is called autonomous consumption, which is kind of the requirement, the basic required consumption, such as like rent. You have to rent, pay rent, and you have to have the minimum, bare minimum, like say water bill, like electricity bill, gas bill, and basic food, and something like that. So these kind of consumptions that you have to pay, even if you don't have any income, is beta zero, autonomous income. And beta 1 is of more interest. Beta 1 is the marginal propensity to consume. So, for example, if you win a lottery and you get additional $1,000, then from that additional $1,000, how much are you going to spend and how much are you going to save? The proportion of saving, proportion of consumption out of those additional income is that ratio is called marginal propensity to consume. This part, beta 1, is also an important parameter in Keynesian macroeconomics because beta 1 determines the multiplier effect, which is the effect of government spending. I don't know if, I believe it should be taught in macroeconomics. So if not, never mind. Anyhow, I just wanted to show you many important parameters that you learned in theory are actually something we estimate. We have to estimate, and they are estimated by some kind of regression models. Of course, model is not this much simple. In practice, the actual estimation is much more complicated and require more data, and we have more data. So it is just an example. It's important. So make the model more general. In general, y is called the dependent variable because it is determined by x. So when you produce a certain output, the cost is determined by the amount of the output. And x is called the independent variable, or sometimes explanatory variable. So by the way, different textbooks use different names. But these notations, I believe, should be similar, especially y and x are common notation. Almost always y is for a dependent variable on the left-hand side, and x is the right-hand side variable that determines y. So we call this independent variable. And beta 0 is a mathematical term. Beta 0 is the intercept. Beta 1 is the slope, or coefficient of x. So constant or coefficient of x. And epsilon is the error term or the disturbance term. So names are not that bad, so more intuitive, more straightforward than other names we learned in earlier chapters. So again, in this general model, our goal is to predict the value of y using x, right? That is what we are going to do. And we are going to make this kind of line. If you estimate the regression model using data, what you are going to do is, so previously you only have 12 dots, but now you can draw the trend line. The trend line is obtained from a regression model, right? All the trend line is obtained from there because this value is the intercept. Exactly, this is what intercept means in mathematics. And the slope, when x increases this much, how much y increases. So this angle, this is the slope. This slope captures beta 1. And then epsilon is the distance, deviation of the observations of the dot from the trend line. the distance is epsilon for each observation. So for example, here there is no error. It's perfectly predicted. And here is a little bit underestimated, and it's overestimated. And yeah, so the trend line is going through the dots. And so again, the parameters are beta 0 and beta 1. We would like to estimate that. And remember, data must have y and x, and they must be paired. Like in the previous chapter, we studied the example of temperature and GDP. You have to know which temperature is for which country and which GDP is for which country. Even if you don't know the country names, still you have to match this temperature is for this GDP. So from this output, we got this much cost. So the data must be paired. X and Y must be paired. And the estimators will be denoted as beta 0 hat, beta 1 hat. So as usual, they are estimators. We are going to use the ordinary least squares estimation method. I will show you the OLS estimator later, but for a while, I'll show you what we can do when you have those estimators. Okay, I'm going to continue in the following video. Thank you for watching this. See you in the next video.